तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We continue our discussion on the transportation problem, and today we look at two methods to get the optimal solution from a starting basic feasible solution. These two methods are called the stepping stone method and the modified distribution method, also called MODI. Now let us look at the stepping stone method. We go back to the familiar example. The three supplies are 40, 60 and 50. The requirements are 20, 30, 50 and 50. The costs are 4, 6, 8, 8, 6, 8, 6, 7, 5, 7, 6, 8. We start with a basic feasible solution. The solution that we start with is given here: 20, 20, 50, 10, 10 and 40. You would remember that this is one of the solutions that we obtained using the Vogel's approximation method or penalty cost method. What we need is a basic feasible solution to begin with. It could be obtained through either Northwest corner rule or the minimum cost method or the Vogel's approximation method, but what we need is a basic feasible solution. Now this solution is basic feasible because it satisfies all the supply and demand constraints. The row totals are 40, 60, 50, column totals are 20, 30, 50, 50 respectively. It does not have a loop, it satisfies the non-negativity restriction, it has exactly m plus n minus 1 allocations, it is not degenerate. So we have a non-degenerate basic feasible solution to begin with. The cost corresponding to this is 80 plus 6 into 20, 120 plus 300 plus 70 plus 70 plus 320, 200, 500, 570, 640 plus 320 is 960. So we have a basic feasible solution with cost 960. Now from this basic feasible solution we would like to go towards the optimal solution. So first thing we need to do is to check whether this is optimal. If this is not optimal, then it is obvious that one of the unallocated positions will have an allocation. So what we try to do is we try to look at every one of the unallocated positions or non-basic positions. Those that are allocated are the basic positions or the basic variables. The non-basic variables in this case are x13, x14, x21, x22, x31 and x33. So we take each one of the non-basic variables or unallocated position and try to make an allocation there. For example, if we try to make an allocation here, which means we put a plus 1 here. Now it means that already there are 6 allocations, now there is a 7th, and any number of allocation greater than m plus n minus 1 this case 7 will have a loop. So we need to identify a loop through this one. So the loop that we have here is as follows. From this plus 1 we go to this, from here we go to this 10, from here we come to this, then we come back to this, and we come back to this, and then we go back to this. So plus 1, 50, 10, 40, 10, 20. Remember, this is also a loop. A loop by definition is starting from any allocation, you move horizontally or vertically and vertically alternately, and then you are able to come back to the starting allocation. This is another loop. Now to balance, we have, if we put a plus 1 here, this will become minus 1, this will become plus 1, this will become minus 1, this becomes plus 1, this becomes minus 1, and it is balanced. So the net increase or decrease in the objective function, as the case may be, is plus 8 because of this, minus 6 because we are taking away 1 from here, so the cost comes down by 6, so minus 6, plus 7, we add 1, so plus 7, minus 8, plus 7, and minus 6. So this is 8 minus 6, 2, 2 plus 7, 9, minus 8, 1, 1 plus 7, 8 minus 6 is 2. So the net increase is 2. So it means that if we consider allocating variable x 1 3, putting a 1 to this position, then the net increase is 2. Now let us look at, it's not x 1 3 equal to 2. So when we enter x 1 3, there is an increase of 2 per unit allocated here. Now we try to put it in the other position. Now we try to put a plus 1 in this position. Now we need to identify a corresponding loop, and the loop is like this, from this to this, here 20 and back. Now this is a loop. Please remember that in a loop, from this plus 1 you do not have to necessarily move into this, you could jump, only thing is you move vertically and come to another position where there is an allocation. So net effect is plus 1 would make a minus 1 here to balance, this minus 1 would make a plus 1 here, and this plus 1 would make a minus 1 here, and the supply and demands are balanced. So the effective increase or decrease, as the case may be, this would give a plus 8, this would give a minus 8, this would give a plus 7, this would give a minus 6, so net is plus 1. So if we consider x 1 4 to enter the basis, we have an increase of plus 1 for a unit increase in this position. Now we look at this position for a possible increase. So we put a plus 1 here. Now we need to identify a loop for this, and let us see how the loop works out. From here we move to this 20, we come back to this 20, then we go to this 10, then we go to this 40, back to this 10, and then back to this, it does not pass through the 50. Now for the balance, this plus 1 would make a minus 1 here, plus 1 here, minus 1 here, plus 1 here, minus 1 here, and balanced. So the net increase or decrease would be plus 6, minus 4, plus 6, minus 7, plus 8, minus 7. So we get 6 minus 4 is 2, 2 plus 6, 8 minus 7 is 1, 1 plus 8, 9 minus 7, 2. So if we consider 2, 1, there is an increase of 2. Now we consider another position, which is this. We consider this position now and put a plus 1 here. Now this would mean we complete a loop starting from this, we go to this position, come down to this position, come back to this 10 and go back again. So the net effect will be this plus 1 would become a minus 1 here, plus 1 here and a minus 1 here, it is still balanced. So the net effect is plus 8, minus 7 from here, plus 8 from here, minus 7 here. So there is a net increase of 2. So if we make the position x2 2 basic, there is an increase of 2. Now there are 2 more positions which need to be tried. So we look at the remaining 2 positions here. Now we try to put a plus 1 in this position. Now we need to make a loop. So from here we move to this, we go back to this, we come back to this position and then we get back. So plus 1 would become a minus 1 here for the balance. Now this minus 1 will become a plus 1 here and this plus 1 will become a minus 1 here, so that supply and demand is balanced. The net would be plus 5 because of this, minus 7 because of this, plus 6 because of this, minus 4 because of this. So effectively the net increase or decrease is 0. So putting x31 would give us an increase of 0 or decrease as the case may be. So we have one more position, which is the last position here. Which this is the last position. So we put a plus 1 here and the loop is like this, from here to this, from this to this, from this to this, from this to this. Please remember that in a loop you have to move horizontally and vertically alternately and switch to positions where there are allocation. So the net effect here would be plus 6, minus 1 here, plus 1 here, minus 1 here. So plus 6 minus 8 plus 7 minus 6. This is 6 minus 8 is minus 2, plus 7 is 5, 5 minus 6 is minus 1. So x32 would give us a decrease of 1. So we have evaluated the trying to enter each one of the non-basic positions, the 6 non-basic positions we have looked at, and then we realize that out of these 6 non-basic positions 1, 2, 3, 4, 5 and 6, we realize that putting a plus 1 here can decrease the objective function, and this is the only position where there is a decrease. There is also another position with 0, which right now we are not considering. So we look at trying to put 1 here. Now when we try to put 1 here, this is the corresponding loop. So we would, per unit allocation here, we know that there is a decrease of 1 possible. So we would like to put as much as possible in this so that we gain as much as we can. So we try to enter a theta here instead of 1, and then we complete the loop. So theta would make this 40 minus theta, 10 plus theta and 50 minus theta. Now we want our theta to be as large as possible, so that we put maximum in this position. So as we keep on increasing theta from 1, 2, we realize that these 2 are going to decrease, this is going to increase. So when theta is 40, this will become 0, and increasing theta beyond 40 would make this negative, which we do not want to happen. So the maximum value that theta takes is 40, which would make this 40, this 10, this 50 and this 0. So this is the next basic feasible solution which we have, and for this solution the cost will now be, the cost associated with this solution will be 80 plus 100 plus 60 plus 350 plus 70 plus 240, which is 200, 260, 610, 680 plus 240 is 920. So there is a reduction of 40, and that 40 is nothing but the product of theta into Cj minus Zj, as we have seen in linear programming. In this case theta was 40, Cj minus Zj was a decrease of 1, so the total decrease is 40, so 960 becomes 920. So now we want to check whether we go through one more iteration and we want to check whether this solution is optimal. To do that, there are now 6 non-basic positions, 1, 2, 3, 4, 5 and 6, and we try to put a plus 1 in each of these positions and evaluate the effect of that. Now that is given by, if we put a plus 1 here, now very quickly completing the loop and proceeding, the loop would be from here to this, here, this and back. So the net effect of the loop will be a plus 8, plus 1, minus 1, plus 1, minus 1 would give us plus 8, minus 6, plus 7, minus 6, which is 2. So if we put in x1 3, there is an increase of 2. And this is the next position. So we put a plus 1 here, and your loop now becomes from here to this, back to this, from this, and over. So plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. The effect will be plus 8 from here, minus 7 from here, plus 6 from this, minus 6 from this, plus 7 from this, minus 6 from this. So 8 minus 7 1, 1 plus 6 7 minus 6 is 1, 1 plus 7 8 minus 6 is 2. So when I put in x1 4, I have increase of 2. Now I look at a third position here. Now this is my third position, so I try to put a plus 1 here, and this is how the loop is, from this to this to here, back to this, goes here and it comes back here. So this plus 1 will become minus 1, plus 1, minus 1, plus 1, minus 1, considering the balance. So the effect will be plus 6 from here, minus 4 from here, plus 6 from here, minus 7 from here, plus 6 from here, minus 6. So 6 minus 4 2, plus 6 8 minus 7 1, 1 plus 6 7 minus 6 1. So putting it in x2 1 would give us an increase of 1. Now let us go back and try the remaining 3 positions quickly. Now let us look at this position and put a plus 1 here. So the loop is like this, minus 1, plus 1, minus 1. So the effect of this will be plus 8 from here, minus 6 from here, plus 6 from here, and minus 7 from here. So this is plus 1. So trying to put it in x2 2 would give an increase of 1. There are still 2 more positions, so we look at both these positions. We look at this position, so we put a plus 1 here, and the loop is like this, minus 1, plus 1, minus 1. So the effect of it will be plus 5, minus 7, plus 6, minus 4, this will become 0. So x 3 1 would give increase but 0, and this is the last position that we will look at. This is the last position, so we put a plus 1 and this is how your loop is, minus 1 plus 1 minus 1. So the effect of this will be plus 8 minus 7 plus 6 minus 6, which is plus 1. So x3 4 would give us increase of 1. Now we realize that there are 6 unallocated or non-basic positions, and putting plus 1 in each would give us increase of 2, 2, 1, 1, 0, 1 respectively. None of them actually are capable of decreasing the objective function further from 920 to something lower than that. So we realize that the optimum is reached. So putting any one of these does not decrease the objective function, so we have reached the optimum. So the optimum solution is found and the present solution is optimal, because we are not able to identify a non-basic variable which can bring down the objective function further. However, we realize that at the optimum that we have found, one of the non-basic variables can contribute a 0 increase or decrease. So this indicates alternate optimum, as we have seen in the simplex algorithm. Presence of a non-basic variable with the 0 value of Cj minus Zj indicates alternate optimum. Now this is a minimization problem. So whatever we have found out here actually is Cj minus Zj, which represents the rate at which the objective function will go up, or in this case go down, because it is a minimization problem, for a unit increase of the non-basic variable. Because we have one non-basic variable which can give us a 0 increase or decrease at the optimum, this indicates alternate optimum, and we try to find out the other alternate optimum solution. To do that, we put a theta here. This is the position that gave us the alternate optimum. So this will become 10 minus theta, 20 plus theta, 20 minus theta. Now as we increase this, we realize that this and this are going to reduce, and the limiting value for theta is 10, beyond which this will become negative. So theta takes value 10, and the alternate optimum would look like this. And the alternate optimum would give us a 10 here, would give us a 40 here, 50 here, 10 here, 20 plus theta will become 30 here, and 20 minus theta will become 10 here. So this is one solution which is alternate optimum, and this is the other alternate optimum. So this is how the stepping stone method works. So in summary, for a given basic feasible solution, stepping stone method tries to enter every one of the unallocated position under the assumption that if the present solution is not optimal, then at least one of the unallocated positions should have an allocation. So stepping stone method tries to do that. It exhaustively looks at all the unallocated positions, and if there is a decrease because of putting a plus 1 in the unallocated position and completing the loop, it enters that and tries to reduce the objective function further. Now at the optimum, when we are unable to find an entering unallocated position, we say that the optimum is reached, which is very similar to saying that I am unable to find an entering variable, or we are finding all Cj minus Zj's positive in this case. For a minimization problem, the positive Cj minus Zj indicates optimum, negative Cj minus Zj would enter. In the previous iteration, we entered a negative value here which indicates a decrease. So we terminate and show the optimum when all the values here are positive. However, the presence of one unallocated position or a non-basic variable with Cj minus Zj 0 indicates alternate optimum, and we can enter that and try to get the alternate optimum solution. Now we will look at a second method which is called the modified distribution method, or the UV method, and we explain the second method using the same example that we have here. So, we reconstruct the problem once again. So, the transportation matrix is like this. Supplies are 40, 60 and 50, demands are 20, 30, 50, 50, costs are 4, 6, 8, 8, 6, 8, 6, 7, 5, 7, 6, 8, and we begin with a basic feasible solution, the same solution with which we started, 20, 20, 50, 10, 10, 40. So, this has Z equal to 960 with which we started. Now, what we are going to do in this UV method or modified distribution method is we try to compute some values of u and v. We associate u1 equal to something, u2 equal to something, u3 equal to something with the 3 supplies, and we also associate v1 equal to something, v2 equal to something, v3 equal to something, v4 equal to something associated with these 4 requirements. Now, for consistency we always put u1 equal to 0. We start with u1 equal to 0, and now we look at the first row. Now, there is an allocation here, the associated cost is 4. So, wherever there is an allocation, now find out either u or v, whichever is to be found out, such that ui plus vj is equal to Cij. In this case Cij is 4, ui is 0, so v1 is 4, 0 plus 4 equal to 4. Now, there is an allocation, there is a 6 here, there is a 0 here, so 0 plus 6 equal to 6, u1 plus v2 equal to C12, and we have x12 has an allocation. Now, we come back to this. Now, because for this allocation 10, Cij is 7, now v2 is 6, therefore u3 is 1. So, 1 plus 6 equal to 7. Now, having found u3 equal to 1, we go back here, we realize there is an allocation here, there is a 1 here, so v4 is 7, 1 plus 7 equal to 8. Now that we have found v4, there is an allocation here, there is a 7 here, so 7 plus 0 equal to 7. And now we have an allocation here with a 6, there is a 0 here, so v3 is 6, 0 plus 6 equal to 6. Now we have 7 variables, but we fixed one of them to 0. So, we have 6 variables to find out, we have 6 allocations, and because it does not have a loop, these 6 are independent allocations, and therefore, we will be able to find out the ui's and the vj's for any given basic feasible solution with independent allocations like what we have done. Now, for all the unallocated positions, these 6 positions that we have, find out Cij minus ui plus vj. Now, for this one ui plus vj is 0 plus 6, 6, 8 minus 6 is 2. So, Cij minus ui plus vj is 2. 0 plus 7, ui plus vj is 7, 8 minus 7 is 1. Ui plus vj is 4, 6 minus 4, 2. Ui plus vj is 6, 8 minus 6, 2. Ui plus vj is 5, 5 minus 5, 0. Ui plus vj is 7, 6 minus 7 is minus 1. So, what we have found, which is Cij equal to ui, what we have found Cij minus ui plus vj is like a Cj minus Zj corresponding to every non-basic variable. You will also observe, if you go back to the stepping stone method, that whatever we found out as the net increase is exactly the Cij minus Ui plus Vj. You can go back and recollect that we computed the net increase or decrease corresponding to each one of them, and we got this. For example, just to illustrate one of these computations, if we had taken, for example, this, if we had taken this, then your loop would have been from here to this, this to this, this to this, this to this, this to this and back. So your net would be a plus 8 from here, minus 6 because of this, plus 7 from here, minus 8 because of this, plus 7 from here and minus 6 because of this. 8 minus 6 2, 2 plus 7 9, 9 minus 8 1 plus 7 8 minus 6 same 2. So what we have found out as Cij minus Ui plus Vj or Cj minus Zj is the net increase when we put a plus 1 in this position. Now out of these, this is the one which has minus. Now this increase, this indicates a decrease, and this variable can enter. Looking at it as Cj minus Zj, for a minimization problem, a negative Cj minus Zj will enter. In simplex we have seen, for a maximization problem, positive Cj minus Zj will enter. For a minimization problem, negative Cj minus Zj will enter. So this variable enters. Now this variable enters, we indicate a theta to find out the extent of entry, the extent to which we can increase this variable. To do that, now we have to go back and compute a loop. So this is the loop. So this theta would mean 40 minus theta, 10 plus theta, 50 minus theta. Now as theta increases, these two decrease. So the limiting value of theta is 40, beyond which this will become negative. So we go back and redo this table again. Forty, 60, 50, 30, 50, 50, 4, 6, 8, 8, 6, 8, 6, 7, 5, 7, 6, 8. So the new basic feasible solution would have a 20 here, 20 here. Now theta being 40, 50 minus 40 is 10, 10 plus theta will make it 50, this will become 0 and this will become 40, and this will remain as 10. So this is the new basic feasible solution, and if we find out the cost associated with this, 80 plus 120 is 200, 260, 260 plus 350 is 610, 680, 920. So the cost associated with this is 920, cost associated with the earlier one was 960, there is a gain of 40, and in linear programming the gain is the product of Cj minus Zj and theta. Cj minus Zj is 1 or minus 1 in this case, theta is 40, so the net decrease is 40, so 960 becomes 920. Now we want to check whether this is optimal using the UV method. So we start with u1 equal to 0 always. Now there is an allocation here, this would give us v1 equal to 4, 0 plus 4 is 4. Now there is an allocation here, therefore v2 is 6, 0 plus 6 is 6. Now once we have found out v2, we go back vertically here, there is an allocation and a 7, so u3 is 1, 6 plus 1 is 7. Now having found u3, there is an allocation here, there is a 6 here, so v3 is 5, 5 plus 1 is 6. Now having found this v3, come back to this, there is an allocation here, total is 6, u2 is 1. And once we have u2 is 1, you go back here, there is an allocation and 7, there is a v4 equal to 6. So we have found out all our ui's and vj's. Now find out Cij minus ui plus vj for all the non-basic or unallocated positions. Now these are the basic or allocated positions. For the non-basic variable or unallocated position, find out Cij minus ui plus vj. 0 plus 5, 5, 8 minus 5 is 3. 0 plus 6 is 6, 1 plus 5 is 6, 6 is 7, 1 plus 6 is 7, 1, 5, 7, 6, 8. Okay. Now 0 plus 6, 6, so you get a 2 here, 4 plus 1, 5, you get a 1 here, 1 plus 6, 7, so you get a 1 here, 1 plus 4, 5, 5 minus 5 is 0, 1 plus 6, 7, 8 minus 7, 1. Now we find that all Cij minus ui plus vj are positive with 1 0, there is no negative Cij minus ui plus vj. So there is no entering variable, or every non-basic variable taken individually is not capable of decreasing the objective function further. So we say that the optimum solution is reached because all the Cij minus ui plus vj's are greater than or equal to 0. For a minimization problem, Cj minus Zj positive indicates optimality. But once again there is a Cij minus ui plus vj with 0 at the optimum, so it indicates alternate optimum. So we try to find out that alternate optimum to put a theta here. So when we put a theta here, now this is the loop. So this will become 10 minus theta, 20 plus theta, and 20 minus theta. Now this will become a new solution, which is this. So we will go back here and we can easily create so now this 40 will remain as 40, there will be a 50 here, there will be a 10 here. Now this theta becomes 10, 10 minus theta is 0, 20 plus theta will become 30, 20 minus theta will become 10. So this is the other optimal solution, same solution that we saw using the stepping stone method. So this is called the UV method or the modified distribution method. One could use both, either the UV method or the modified or the stepping stone method. One could use any one of them, but consistently we use the UV method, and we later try to show why the UV method is desirable as the problem size increases. Now let us look at one more example to show how we get the optimal solution here. Now we take a case which has a degenerate basic feasible solution. We have already seen that we could have a degenerate basic feasible solution. A degenerate basic feasible solution is one where we have fewer than m plus n minus 1 allocations. So let us take an example with the degenerate basic feasible solution for the same problem that we have used. So let us look at supplies are 40, 60 and 50, requirements are 20, 30, 50 and 50, and these are 4, 6, 8, 8, 6, 8, 6, 7, 5, 7, 6, 8, and we look at a different allocation for the degenerate basic feasible solution. let us look at this solution which has a 20, 20, 10, 50 and 50. Now let us look at this basic feasible solution to the transportation problem. Now this is basic feasible. The row sums are 40, 60 and 50 respectively. Column sums are 20, 30, 50 and 50 respectively. Now this is degenerate because we have 5 allocations, m plus n minus 1 is 6. Now the cost associated with this is 80 plus 120 is 200, 280 plus 300 is 580, 580 plus 400 is 980. Now let us try to solve this problem using the UV method. So we first put U1 equal to 0 would give us V1 equal to 4. Now there is an allocation here, so this would give us V2 equal to 6, so that 0 plus 6 is 6. Now there is an allocation here, so we get U2 equal to 2, 6 plus 2 equal to 8. There is an allocation here, so we get V3 equal to 4, 4 plus 2 equal to 6. Now here we do not have, having identified this V3 equal to 4, we do not have another allocation here which would give us this. Now to do that, we need to put one presently, all these 1, 2, 3, 4, 5, 6 positions are unallocated. There are 7, 1, 2, 3, 4, 5, 6, 7 positions that are unallocated, and we need to identify a place from which we will be able to compute either U3 or V4. So to do that, we try to put an epsilon, for example, in this position. We try to put an epsilon in this position, so that this is 4. Now we assume that epsilon equal to 0 is an allocation, so U3 will now become 2, so 4 plus 2 equal to 6. And now that we have an allocation here, 2 plus 6, V4 will be 6, 2 plus 6 is equal to 8. So whenever we have a degenerate basic feasible solution, which means we have one allocation less than what we normally have, we need to put an epsilon in a particular place so that we are able to get the u's and the v's. And we have to be very careful that we do not put epsilon in the wrong place. Epsilon should retain the fact that these 6 positions are independent. For example, if we had put an epsilon here, then we realize that this would already mean a loop. An epsilon 50, 10 and 20 would create a loop, and if there is a loop, there will be inconsistency in the u's and the v's. If we had put the epsilon here, then you realize that 0 plus 4 is not equal to 8, and that is violated. So we have to make sure that the epsilons are put in such a way that they are independent, and we are able to get the u's and v's, and there is no inconsistency with respect to the u's and v's. Now we go back and find out the Cij minus ui plus vj as corresponding to the 6 unallocated positions. So this is 0 plus 4, 4, 8 minus 4 is 4, 0 plus 6 is 6, 8 minus 6 is 2, 2 plus 4 6, we have a 0 here, 2 plus 6 8, so we have a minus 1 here, 2 plus 4 6, we have a minus 1 here, 2 plus 6 8, we have a minus 1 here. So there are 3 places which have a minus 1. Cij minus ui plus vj is minus 1 and so on. We could take any of these positions. There is a tie for 3 positions. We could take any one of these positions. For example, we start with this position. So we identify this as a position that can enter, and we try to put a theta here. So when we try to put a theta here, we need to close the loop. Now this would give us this loop. So this would mean that theta, epsilon minus theta, 50 plus theta and 10 minus theta. This would balance the supply and demand requirement. Now what happens? As we put theta, these two start decreasing. So the smallest value that theta can take is epsilon, beyond which this will become negative. So the value that theta takes is epsilon, and your new solution now becomes four, 6, 8, 8, 6, 8, 6, 7, 5, 7, 6, 8, 20, 20, 10 theta is epsilon, so this becomes 10 minus epsilon, this is 50 plus epsilon, now this is epsilon and this epsilon minus theta becomes 0. Now what is the value of epsilon? When we put an epsilon here, we meant to put an epsilon here to indicate that this position is basic but with value 0. So the epsilon has to be used very judiciously. Now epsilon will take value 0 in this position, but will retain itself as epsilon here, indicating that this is a position where there is an allocation with 0. Now if we go back and evaluate the cost corresponding to this, you will get 200, 280, 280 plus 300 is 580, 580 plus 400 is 980, cost does not change. Cost did not change because Cj minus Zj is 1 or minus 1, but theta was epsilon, which is 0, so the cost did not change. Only thing that effectively happened here was the position of the epsilon got shifted, there was no reduction in the objective function. This is exactly the reason or due to degeneracy. Degeneracy would go through iterations where the objective function value does not reduce for a minimization problem. So typical effect of degeneracy is just a shift of the epsilon. The objective function value remains the same. Now we proceed with this and try to get to the optimum. So u1 equal to 0 would give us v1 equal to 4 based on this, v2 equal to 2 based on this. Coming back, u2 equal to 6, 2 plus 6 equal to 8, there is an allocation here, v3 equal to 0, 0 plus 6 equal to 6. From this u3 equal to 5, 5 plus 2 equal to 7, now from this v4 equal to 3, 5 plus 3 equal to 8. Now find out Cij minus ui plus Vj. Now this is 0 plus 4, 4, sorry, this is 6, 0 plus 4, 4. Now let us compute the u's and the v's again. This is 0, always u1 equal to 0. Now this gives us v1 equal to 4, there is a 6 here, v2 equal to 6. So u2 equal to 2, from here v3 equal to 4, now 6, so this is plus 1 and this is 7, 1 plus 7 equal to 8. So 0 plus 4 is 4, 0 plus 6 is 6, 2 plus 6 is 8, 2 plus 4 is 6, 1 plus 6 7, 1 plus 7 8. Now find out Cij minus ui plus Vj, 0 plus 4 4, 8 minus 4 is 4, 7, 8 minus 7 is 1, 2 plus 4 is 6, 6 minus 6 is 0, 4 plus 1 5, 5 minus 5 is 0, 1 plus 4 5, 6 minus 5 is 1, 2 plus 7 9, 7 minus 9 is minus 2. Now this is the only position that shows a decrease, so we put a theta here and we need to complete the loop. So theta 50 minus theta, epsilon plus theta, 10 minus theta. Now as theta increases, you realize that these two are going to decrease. So the limiting value of theta is 10, beyond which this will become negative. So theta takes value 10 in this, and the new solution becomes 6, 8, 6, 7, 5, 7, 6 and 8. Now the 20 and 20 remain as they are. Now theta is 10, so this becomes 10, 50 minus theta will become 40, epsilon plus theta, epsilon was 0, so 0 plus 10, 10, 10 minus theta will become 0 and we have another 50 here. Now we realize that here we had 5 allocations, 1, 2, 3, 4 and 5, but here we have 6 allocations, we have come back. Now here it has come out of degeneracy. Now this is an example where it has come out of degeneracy, from 5 allocations we have got 6 allocations. Now we can proceed as we normally did towards the optimal solution. The gain would be, now in this case theta is 10, Cij minus Zj is 2, so gain will be 20, so 980 would become 960. From now on we proceed, u1 equal to 0, v1 equal to 4, v2 equal to 6, from here u3 equal to 1, 6 plus 1 7, v4 equal to 7, 7 plus 1 8, u2 equal to 1 or minus, sorry, u2 equal to 0, 0 plus 7 is 7, now v3 equal to 6, 6 plus 0 is 6. Once again 4 plus 0 is 4, 6 plus 0 is 6, 0 plus 6 6, 0 plus 7 7, 1 plus 6 7, 1 plus 7 8. Now find out the Cij minus uy plus vj, 0 plus 6 6, so 8 minus 6 is 2, 8 minus 7 is 1, 4, so you get a 2 here, you get a 0 here, 0 plus 6 6, you get a 2 here, now 6 plus 1 7, you get a minus 1 here. Now there is a minus 1, there is one entering non-basic variable which shows a decrease in the objective function for a minimization problem. So put a theta here. Now the loop will be this 40 minus theta, 10 plus theta, 50 minus theta. Now once again as we increase theta, these two decrease, so the limiting value of theta is 40. Now the new solution will become four, 6, 8, 8, 6, 8, 6, 7, 5, 7, 6, 8. The new solution, we have a 20 here, we have a 20 here, we have a 10 here. Now theta is 40, so this becomes 0. 10 plus theta will become 50, 50 minus 40 will become 10, and this theta is 40. Now the Cj minus Zj is minus 1, theta is 40, so there is a further reduction of 40. So 980 had already become 960, 960 minus 40 is 920. Now that is given by 80 plus 120, 200, 260, 610, 680 plus 240 is 920. Now once again finding ui's and vj's, we have 6 allocations, so we do not worry about degeneracy. So u1 equal to 0, v1 equal to 4 from this, v2 equal to 6 from this u3 equal to 1, 6 plus 1 is 7, from here v3 equal to 5, 5 plus 1 is 6, from here u2 equal to 1, 5 plus 1 is 6, v4 equal to 6, 6 plus 1 is 7. Once again verifying, 0 plus 4 4, there is an allocation, 0 plus 6 6 allocation, 1 plus 5 6, there is an allocation, 1 plus 6 7 allocation, 1 plus 6 7 and 1 plus 5 6. Now once again finding Cij minus ui plus vj, 0 plus 5 5, 8 minus 5 is 3, 0 plus 6 6, 8 minus 6 is 2, 1 plus 4 5, 6 minus 5 is 1, 1 plus 6 7, 8 minus 7 is 1, 1 plus 4 5, 5 minus 5 is 0, and 1 plus 6 7, 8 minus 7 is 1. Now all Cij minus Ui plus Vj, none of them are negative, all of them are positive or 0. Now this indicates optimum, the same optimum solution that we had. Now this indicates optimum because there is no non-basic variable or a non-allocated column or a potential entering variable that can reduce the objective function further. However, we realize, as we did earlier, that there is one non-basic variable or unallocated position which has a Cij minus Ui plus Vj or Cj minus Zj value of 0 at the optimum. So this once again indicates alternate optimum as we had seen. So we evaluate the alternate optimum by trying to put a theta here. Now we once again complete the loop. So this theta would mean this as the loop. So 10 minus theta, 20 plus theta and 20 minus theta. So the new solution will look like this. So this 40 will remain as 40, 10, 50, theta is 10 because once again as we increase theta, these two values reduce and the limiting value is 10 beyond which this will become negative. So theta is 10, 20 plus 10 is 30 and 20 minus theta is 10. So we once again have a solution with 6 allocations, once again with the same 920, 40, 6, 6, 7, 6 and 5. So this is 40 plus 180 is 220, 220 plus 60 is 280, 280 plus 350 is 630, 630 plus 50 is 680, 680 plus 240 is 920. So once again same value because alternate optimum Cj minus Zj was 0 even though theta was 10. So the value is the same 920 from this. So this is how we solve the problem if we have a degenerate basic feasible solution. Now we began this example with a degenerate basic feasible solution and we saw a couple of things. We saw in one iteration that the epsilon merely shifted its position. Every degenerate basic feasible solution would require an epsilon. An epsilon is necessary to get the m plus n minus 1th position or the missing position. The epsilon should be put in such a way that we are able to get the u's and the v's to retain the independence of the allocations, making sure that there is no inconsistency in evaluating the u's and the v's. So we need to put the epsilon in that manner. Because of degeneracy, we could get into situations where there will not be a decrease in the objective function in a subsequent iteration and the position of epsilon will change. Now that can happen when after we introduce a theta, we get an epsilon minus theta in one position. There we have to be very careful and to shift the position of epsilon from one to another, rest of the allocations will remain. We could also have situations where the problem comes out of degeneracy by itself, as we saw. We had 5 allocations and somewhere we got the 6th one. So that will happen sometimes when we have an epsilon plus theta coming in as we put the theta and close the loop. Now if the problem has an alternate optimum, then at the optimum, that is when all the Cij minus Ui plus Vj's are strictly positive, there will be one Cij minus Ui plus Vj with 0 which will enter and it will give us the alternate optimum. So what we have seen today are the two methods, the stepping stone method and the modified distribution method, also called the UV method, and we also saw how we handle problems with degenerate basic feasible solutions using the UV method. We continue our discussion and compare these two methods in the next lecture.